Okay, can you hear me this time? I do have a green. I haven't got any participants, so let's have a share and go into WhatsApp and have another go. Right then, is anybody there? Can you hear me? Yep, I can. Can I boost the volume? All right. Okay. Yes, you can hear me. That's good. Right then. So I've just sent out. Okay, I'll just do it by email as well, in case we've got in the WhatsApp group. So I just find my sent items, and right. Okay, so I've just invited some more people. I've got 7 people now, so I'm going to go back to playing with my small plastic toy just for a moment, and then it's about in a few minutes when we've seen how many participants we've got. We'll have a go at doing the questions. Okay, so my question was, does anyone know what toy that is? Because that is, into toys, that is one of the massively iconic toys, and when I show you what it can do, you'll be frankly amazed. Okay, I'll just do some visual effects for you. 5, 4, 3, 2, 1. No, not helping. So let me just show you some of the things it can do. Okay, so I need to wait for it to land on, really, so that you can, without it going out of view. I just have to do a mid-air. Okay, so you press this button, and then that's right. Then out of there comes this little podule. And then inside there is they put other different things in it. That's the mole, and it could dig underground for rescuing people underground, or you could put a mini submarine in there. And this is Thunderbird 2 from the famous Thunderbird series. Right, that's enough messing about. Does anybody have any questions about the homework? I've got the homework questions available, so if you tell me what you're stuck on and anything like that, and I will do my best to help. Anybody? How's the weather with you? Very sunny here. Thank you very much. Good to see you. I'm not suffering from the quality too much, really. Quite, bit of cooking pizza, going for bike rides. Okay, so I'm going to get a bit of paper. Okay, let's get a new bit of paper. We don't care about how much it costs. We're just going to go for a whole new sheet of paper. So 3C, we've had a request for. 2 plus 4. Hi there, Mel Easy. And so I think let me just, I'll have to just go to a different, now what I should do, if I was an intelligent teacher, and I'm vaguely intelligent, I'm just going to tile you the view of me against, if I open in here, Oh, there they are. Right. We get the questions in here. Be there in a moment, honestly. So we're going to start with question 3C. Right. The surface of cesium is exposed to photons emitted in each of the three transitions shown in the diagram. The threshold frequency of cesium is 5.1 times 10 to the 14 hertz. Determine whether any of these transitions would produce the photons that cause electrons to be emitted from the cesium surface. Right. Okay, well, we can deal with that. So we need to go back up to the diagram. Now, if you remember last time when we tried to do a bit of teaching like this, we had difficulty because we couldn't get the writing the right way around. So I flashed out, just wait for it, £4.87. Yeah, I'll just say that again. £4. I have the lead the wrong way around. 87p. So that we can now have the writing the right way around by going for the full paid version for the app. Okay. However, possibly I could have anticipated a little further in advance exactly how we wanted the camera arranged. I don't need a keyboard at the moment. Okay, so let's have a look. Well, that's a bit weird, isn't it? Because it's the right way around for me, but that's clearly complete. But now you see I can. All right, okay, so that's good, is it? You can see that now, can you? So what I just need to do, I was going to print this, but I realized I couldn't quite afford the costs of all the printing involved. So we've got n equals 1, 2, 3, 4. 1, 2, 3, 4. And these are labeled minus 13.6 EV, minus 3.4 EV, minus 1.5 EV, and minus 0.85 EV. And the question was, the surface of cesium exposed to photons emitted in each of the transitions shown in the diagram. Okay, so the transitions were A, B, and C, and we've got to know, and we've got a threshold frequency. What was it? 5.1 times 10 to the 14 hertz. I don't mind answering this question, but in terms of how difficult it is to put the information across without a printed version of the thing, this is about as difficult as it gets. Is that backwards for you? It's backwards, right? You mean it's the wrong way around, left to right? Right, okay. Is that better? Is that now the correct way round? Good, excellent. Sorry about that, but luckily with the paid app, it's very easy to sort out. It is very confusing because on my YouTube screen, that is now the wrong way around. So, I'm just checking we haven't done any prior calculations. No, we haven't. So what we need to know is, is that still working? Yeah, sorry. What we need to know is the energy of the photon emitted by any of those transitions, is the frequency greater than 5.1 times 10 to the 14 hertz. Now, the one that's most likely to be is this transition here. And there are two ways you could tackle this program. My first thought was I'm going to find the energy difference in electron volts. Then I'm going to convert that to joules, and I've even got my calculator handy, and I think I know where a date sheet is, so it's fairly easy. And then we'll see if the frequency is greater than that. The next thing we could do, but then we would, if it was, and I suspect it will be, we'd have to check B separately. So what I'm actually going to do is I'm going to do it the other way around. I'm going to convert that frequency into an energy in electron volts, and then I can compare it to each of the gaps, because I think overall that will be less calculation. So we've just got to do E equals HF. So that's 5.1 times 10 to the 14 times 6.63 times 10 to the 34. 5.1 x 14 times 6.63 x minus 34 equals 3.38 times 10 to the minus 19 joules. Then the next step, I've got to convert that into electron volts, and the way that I do that is by dividing by 1.6 times 10 to the minus 16. Sorry, 1.6 times 10 to the minus 19. So 3.38 x minus 19 divided by 1.6 x minus 19 equals 2.1 electron volts. Now we go back up here. This gap here is virtually 10 electron volts. So we can definitely say transition C, because 10 electron volts is more than 2.1, will liberate an electron. This gap here, we just do it on a calculator to make sure I don't get it wrong. 3.4 minus 1.5 equals 1.9. 2.1 is more than 1.9, so this B could also liberate an electron. The gap here is clearly less than 2, so hang on a moment, did I say that the wrong way around, or didn't I? The energy of this photon is 1.9 electron volts. That's less than the energy required to remove an electron, which is 2.1. So C will, B won't, and if B won't, A won't. So it doesn't actually matter which way round you did that calculation. And 3B, okay. Two ways to excite a hydrogen atom are by collision with a free electron or by the photon. Explain with a particular why for a particular transition the photon energy, whereas the free electron by an electron. This electron comes along and it transfers some of its energy to the electron, and then off it goes. I just realized I don't know whether this is in focus, so I'll just hit the AF button for you. Hopefully that's better. Give some of its energy here, as much as is required, and then it goes off and it carries away any spare energy. So provided this has got enough energy, it can always give some energy here. So change pen color. If you have that comes along and it hits that electron, then it has to give all of its energy, because it ceases to exist. It gives up its energy by ceasing to exist and giving all of its energy across. That means that if it hasn't got exactly the right amount of energy, there's nowhere for the spare energy to go, so that the process is not allowed. Okay, hopefully you found that useful. I was also asked to go through questions 2 and 6. Okay, so yeah, but I think it is. So is it all of question 2? So I think the A is just a matter of doing yeah, I will go on to 4. I think going back up the list, Sidra said, I think SS is Sidra said 2 and 4. So I'm just personally looking at 2. So 2A, I think is a simple matter of mgh equals a half mv squared. So then it asks you to discuss the difference of acceleration. So In question 1A, the trolley goes down a ramp this shape, and in the second ramp, the second question, the ramp is that shape. So this has got a constant, if there are no resistance forces, this has got a constant acceleration because the component of the weight down the slope doesn't change. Here, initially you have a higher acceleration because the ramp is steeper, then the acceleration becomes less and less and less until it becomes zero here. Whereas here it's constant until it gets to the level and it suddenly becomes zero. C, I think, is just a matter of realizing that the speed is exactly the same because it's moved through the same vertical distance. And then the last part is a slightly difficult conservation of momentum question. So what it says is that you've got a trolley moving along this way. It's got a certain amount of momentum mv, and momentum is a conserved quantity in a closed system. So as rain falls into the trolley, the total mv must remain constant. M is increasing and therefore V is decreasing. Do I need to say anything more about question 2? Right, I shall have a quick look at question 4. I do think question 4 is a bit difficult. I'll whiz through the ones I can discuss, and then we'll get on to kind of drawing a diagram and doing the resolving. So 2 conditions for equilibrium. Vector sum of all forces is 0, and the sum of clockwise moments is equal to the sum of clockwise moments. The center of mass is the point in the object where the weight appears to act. And thank you for confirming that question 2 is okay. Explain why the center of mass of the beam in the diagram must be vertically below A. What we've got here, I'll just make sure I give a really good copy of the diagram. I don't know who Jeffrey was, but they're not with us anymore. So the question is, why does the center of gravity? Because if there can be no resultant moment if this is in equilibrium and around any point, and this easy one is consider is that point there. So if the center of gravity was over here, it would have a clockwise moment turning the beam, and that would turn it underneath. So it's to make sure there is no resultant moment. The weight of the beam is 12,000 newtons. Calculate the tensions in T1 and T2. Now, I'll just make sure I've got T1 and T2 correctly labelled on my diagram. I'll try and remember to write really big. So, yeah, AB is. There are 2 separate ways of doing this. One is more using simultaneous equations, and the other is it involves more. Let's go down the simultaneous equation route to start with. So what we know is that the vertical component of T1 plus the vertical component of T2 must equal 12,000. So if we take T1 there, that angle there is 37 degrees. The vertical component, because that's the adjacent side, is T1 cos 37. So T1 cos 37, just down the S, plus the vertical component of that one, T2 cos, sorry, that's 53, plus T2 cos 37 must be equal to 12,000. But I'm sure you know that that's not enough information to solve the question. So yeah, and then we need another equation, don't we? Because you've got two unknowns and only one equation. I'm not going to solve these for you. You're better at doing that than me. I'm out of practice with all that. Is that the two horizontal components must be equal to each other. And I suspect that that's how most students will solve it. But there is another way as well. We know that we've got three forces acting in the diagram on the beam, 12,000 newtons downwards, plus T1, making that angle there 53 degrees, plus, remember when we add vectors, we draw them end to end, T2, and then that angle there, so that angle there is 37 degrees. That makes that angle there 37 degrees by Z angles. That's a right angle triangle. So now we have a right angle triangle with known angles and known sides. So we can go about finding. Okay, I'll come to your question in a moment, Maliha. So we've got a simple solution of a right angle triangle there. The reason is because there must be no resultant force vertically or horizontally. So vertically, forces up equals forces down. Horizontally, forces left equals forces right. If either of those component was bigger than the other, then the beam would accelerate off horizontally. So hopefully that's okay. I'll just pause for a moment and see if any more questions come up. And then I think we're on to question 6C. So let me just get my head around that. Does that mean that you're all right on the rest of question 6? Right, I'm moving on to question 6 then. Right, question 6C. The lamp in Jeffrey, last chance, because really I need to just focus on teaching physics and not dealing with people who want to talk about other things. So so 6C, lamp B fails. This does not change the effect, the resistance of the other lamps. Deduce the effect on the current in the battery. Use calculations to support your answers. I'm just scrolling back up to find the answer. Fair enough, Maliha. I'll go through 6 from the beginning. I think that makes total sense. So we'll come back to that in a moment. Got A, B, A, B. Now, obviously, I'm a veteran of these sorts of questions, and my hunch is that it's as much to do with the words as the diagram. Okay, so I'm just going to pause and read it aloud to you because I think there'll be some really important information. A student connects a A student connects 4 lamps A, B, C, and D in the circuit shown in figure 1. The battery has an EMF of 9 volts and negligible internal resistance. The table when they are at normal brightness. The student observes that 2 of the lamps are at their normal brightness. Assume that any change in resistance to the lamps are negligible. Okay, so for to do over Eastern, I've just put into the message there's a URL, and if you just copy and paste that into any browser, it will show you the questions. But that's sorted now. So there's 6 volts, 6 watts, 3.5 volts, 4.1 watts, and that they're working with their normal resistance. Which 2 bulbs are at their normal resistance? So we know that A and C are the 6 volt bulbs, and B and D are the 3.5 volt bulbs. We know that the power is 6 watts and 6 watts, so and 4.1 watts and 4.1 watts. Actually, this is a reasonably difficult question. So my hunch is that I'm trying to think if I can do it without going through how many marks is it without having to work out each resistance. Yeah, I think we need to work out the resistance of each bulb. So V is equal to IR, R is equal to V over I. And so for the one on the left, we know we would have 6 volts and 6 amps. So we have 1 ohm. Let's grab another colour. So that's 1 ohm and that's 1 ohm. We're then going to use P equals IV, I equals P over V to find out how much current would need to be supplied to the to this bulb. So it's 4.1 divide 3.5 equals. So that's a current of 1.171. So the resistance will be 3.5 volts over 1.171 dot. So I think that gives 2.987. That's a really annoying amount of resistance, isn't it? Because you never know when whether the exam board meant that to be 3 or not. But the answer must be, so that gives a total resistance of 8 ohms in each branch. No, 4 right, yeah, 4 ohms in each branch. Yeah, the answer must be that bulbs A and C are at their normal brightness, because if they got if the current is 1 amp, which is what's required, there are 2 options, aren't there? Either the current is 1.171 amps to make these 2 their normal brightness and make that 3.5 volts, that would be then more that than 6 volts, because we have a resistance of no, sorry, got it now. Yeah, these are both 6 ohms, aren't they? So where I went wrong there is V is 6, but I is 1. So those are 6 ohms. So if there's 1 amp, that's 6 volts. That's 3 volts. That adds up to 9 volts. So it must be that way around. So A and C are normal brightness, B and C are dimmer. Because if we had a current of 1.17, that would be 3.5 volts. That would be over 6, and it'd add up to over 9. So that's the answer to A. Okay, so then we get B. Explain what the bright student we observe. So we're adding a bulb here. Now, to me, this bit is fairly straightforward, but maybe this isn't to you. Because that pair of bulbs and that pair of bulbs are the same in the same ratio, whatever the voltage is here, the voltage is here is the same. So there's going to be no current in this bulb and no voltage in that bulb. I expected to do a calculation. Because of the ratio of these two resistances is the same, the potential difference here and the potential difference here are the same. The potential difference here and here are exactly the same. There's 0 difference between them. There's 0 difference. There'll be 0 current and the bulb won't light. And then now we're back to lamp B failing so that it no longer cuts. This does not change the effect, does not affect the resistance of the other lamps. Deduce the effect on the current in the battery. Use calculations to support your answer. So we're losing that one there. So we have to think through. I think I'm going to have to redraw the circuit to illustrate what we've now got. So we've got a 9-volt battery that comes along, and then we've got our bulb here, which is our 6 ohm resistance bulb. I think that's the most useful piece of information. Then we've got our other 6 ohm bulb up there, and then it goes through bulb E in parallel, and then we come to bulb, and that's A, C, E, and D, and it comes back round like that. And I've just got to check what that middle lamp is. Right, so that's a debit. So this resistor. Deduce the effect on the current in the battery. But first of all, we know that the current, because we had 1 amp here and 1 amp here, the current through the battery was 2 amps. Now we've got to see through what the current in the battery is, and that's 3 ohms. So what we've got to do is deal with, first of all, the smallest structure is here. So we've got to make that into 12 ohms, and that's 6 ohms, and they're in parallel. So you've got 1 over R equals a 6th plus a 12th, which is 3/12. So R is 12 over 3, which is 4 ohms. 4 ohms plus 3 ohms. 3 ohms is 7 ohms. And then it's just a matter of working out the current using V equals IR. Okay. So I'm just trying to keep going in order. So I've had just had a request for 9C. I'm just going back to see what else. I've had requests for 10. Yeah, so 9C is our next port of call. A radioactive source emits alpha particles. The alpha particle. Right, okay, so this is quite a good example of a question to go through. It's just kind of a deduction question, really. So it says an alpha particle transfers all its kinetic energy to air molecules and produces 5.1 times 10 to the 14 ions per centimetre over a range of 3.5 centimetres. Calculate the average ionisation energy in EV of a molecule of air. So if every time it goes through a centimetre of air, it produces 5.1 times 10 to the 4 ion pairs, and it does that over 3.5 centimetres, the number of ion pairs is 3.5 times 5.1 times 10 to the 4. So the kinetic energy in the alpha particle is enough to make that many ion pairs. So then I'm just scrolling back to find out how much energy the alpha particle actually had. The alpha particle's got energy 8.1 times 10 to the minus 13 joules. So at some point we've got to convert to electron volts. So to convert that to electron volts, we divide by 1.6 times 10 to the minus 19 joules, which is obviously going to go in about 1,000,000 times. And then we've got to divide that energy by the number of ion pairs we made, which is this number here, 3.5 times 5.1 times 10 to the 4. Is dividing by that number there. And then we can use the fraction button on our calculators to put all that together. 8.1 x minus 13 on the top, 1.6 x minus 19 times 3.5 times 5.1 x 4. I'll just pause and see if I've got anything wrong. Don't think so. So the answer is 28.4 electron volts. Is it a 3 significant figure question or a 4? It's sorry, 3. It's so we'll make that 28 electron volts, which is certainly the right order of magnitude. So, and then we were asked for some questions about 10. Am I going through 10 from the beginning? Somebody who asked about 10, or am I just going through 10 of it? 10B and 10C. Well, we'll have a quick look at A then as we go along. Let's grab some more paper. Right. So yeah. So the first one isn't too difficult because it's just a matter of using this subtracting 3.2552%. I wonder if we're going to need that later on. A wiser teacher might have had access to the questions at this point. Give your answer to an appropriate or significant figures. Speed of light in a vacuum is 2.998 times 10 to the 8. Right, so I've not seen this before. That's quite interesting. So we've got a standing wave forming in the core of the fiber optic. We've got bright spots because of waves traveling in opposite directions. A cable is used to raise and lower a lift. An engineer fixes the optical fiber strain gauge to the cable to monitor changes of the strain in the cable. The lift is initially at rest and accelerates downwards for a short time before reaching a constant velocity. Discuss how the value of YR changes. Right, so that's quite an involved question. Let's just sketch the graph. So we've got YR against strain, which can be seen as force. And then what we need to do to be able to answer the question, we've got to think about how the force in the cable will change. So the initial lift is initially at rest. So if I plot a graph of force against time for the lift, then initially there's a force equal to its weight. It then accelerates downwards for a short time before reaching constant velocity. So to accelerate downwards, here's our lift. We've got weight acting up, acting down, and we've got tension acting up. To accelerate downwards, we must have resultant force down, so the tension becomes less momentarily. So it drops down, and then accelerates downwards for a short time before reaching a constant velocity. So if it reaches a constant velocity, the force must go back to being equal to the original weight again. What I can't see is whether there's how it will transition between the two. So I think we're just going to go like that and assume that the acceleration is getting less and less and less with time. Now, so what we can see is, in terms of what will happen with lambda r? Well, when strain or force increases, lambda r increases. So initially we will have a certain value of lambda r, and then when the lift starts to accelerate downwards, that lambda r will decrease, and then it will increase again back to its original value. Right. Did I do 9C? Yes, done that. Sorry. Figure 4 shows the relationship between YR and the strain in two optical strain gauges, P and Q. The engineer wishes to measure small accelerations in another lift. She can choose to fix either optical strain gauge P or Q to the lift's cable. Explain which gauge the engineer should select. I'm assuming the answer is that you select P. Let's quickly sketch it because you might not be able to see this. You've got two cables. This is lambda R. This is strain, Q and P. And I think the answer is PB because the change in strain produces a bigger change in P, and therefore we have a more sensitive piece of measuring apparatus. So if a small change in strain will have a bigger effect on P than Q because it has a greater gradient. Right, so that's question done. 9E, 9 missed one out. Oh my goodness, right. Discuss how the potential difference across the air gap varied as the radioactive source was moved over this distance. Assume the power supply has negligible internal resistance. I'm not going to do that. And I think the reason I'm not going to do it is because I think it involves knowing about the ranging out of alpha in air. And I think that that's something that we're not going to do. The next one, so we're going to leave 9E. Ah, right, 18 is a multiple choice. I thought, crikey, how many questions is that? Measurements are made to determine length and mass per unit length of a string stretched between two supports. The percentage uncertainties in these measurements are shown. A stationary wave is formed on the string. What is the percentage uncertainty? Excellent. So I'm just going to find a data sheet. Right, got one. So what we need to do is find the equation for wave equation. So the equation for the frequency of the first harmonic is F is equal to 1 over 2L root T over mu. Now, the crucial thing that's going on here is that the percentage uncertainty in F will be the percentage uncertainty in L plus half the percentage uncertainty in T plus half the percentage uncertainty in mu. Let me try and explain why. It's because T over mu is to the power of half. And if you remember, I said that if there was an uncertainty in X of X%, then if you square it, you get X squared plus or minus 2X%. So the power is a multiplier on the percentage uncertainty. And when you multiply two things, you hold up their percentage uncertainty. So we're told length is 0.8%. We're told T is 4%, halve it to give 2. We're told that mass per unit length is 2%, so that gives 1%. So you add those all up, 3.8%, so that so the answer is B. Maliha, you can leave 9E because we haven't done it. Okay. And then I was asked for question 21. The fundamental frequency F is the lowest frequency heard when a stretched string is vibrating. The string is now lightly touched 1/3 of the way along its length. What is the lowest frequency heard? Right. We need a diagram. So this is the fundamental frequency. The lowest possible standing wave that can exist there, and that's got frequency F, and that is half a wavelength between the two nodes. So what they're saying is, if you, I can't really draw this very neatly, but it might not do my best. If somebody puts their finger here 1/3 of the way along, that forces that to be a node, and if we're forced to have a node here, then we will form that pattern. So now that's lambda over 2. So the wavelength is now gone down by, we've divided the wavelength by 3. It's 3 times left. The wave speed is constant, C equals F lambda. If that is 3 times left, that's 3 times more. So the answer is D. Okay, are we going to stop there? Because that seems like I've been going for quite a long time. Yeah, 50 minutes. But I will just pause and say any final questions. Right, folks. Thank you very much indeed. I shall sign off there then. Okay, I'll just give you one more moment just in case you're typing. 23. Feels like the end of an auction. 2 points on a, oh, right, this is a good question. 2 points on 2 points on a progressive wave have a phase distance of pi by 6. Actually, this could take quite a lot of explaining, but it will be quite useful if I can explain this. So if we imagine a wave like this, those 2 points are one wavelength apart, and they have a phase difference of 2 pi because they're in phase. Those 2 points are half a wavelength apart, and they have a phase difference of pi. You divide that by 2, and we divide that by 2. So if we have a phase difference of pi by 6, that's 6 times less, then the wave length, the distance between them, is also 6 times less. That's pi by 12. That's lambda by 12, the wavelength divided by 12. So if lambda over 12 equals 0.12 meters, lambda equals 0.12 times 12, which probably is 1.44 meters, isn't it? Well, if we don't get an answer that's there, we'll have to actually check the maths. And the speed of the wave is 340, so C is equal to F lambda. So it's 340 equals F 1.44, so F is 340 over 1.44. 340 divide 1.44 equals 236. So the answer is A, 240 hertz. 30. The graph shows how the resultant force F on a football, which is initially at rest, varies with time. Which graph shows how the momentum P of the football varies with time T? So it's a kind of accumulation of the area, isn't it? So as you sum the area represents how much the momentum the ball has gained at that time. So initially it goes up steeply, and then it goes up more slowly. So the answer must be B. Yeah. So it starts, the momentum of the football starts going up at a particular rate because the force is going up. Ah, no, but is it a curve or is it a straight line? No, it's a curve, isn't it? Because if I go to there one time interval later, that's 4 times the area. So if you go from T to 2T, you get 4 times the area. So therefore it's not a linear relationship. So sorry, the answer is D. So it grows faster and faster and faster as the force increases, then slower and slower and slower as the force decreases. That's 30. So Maliha has asked, how there are 2 K neutral mesons. What is the quark conjugate of the kaon? And will all contain either a strange or an anti-strange quark, and either an up or an anti-up, or a down or an anti-down, and you have to have either a strange or an anti-strange. So you can have strange, strange, anti-strange, anti-strange. You can have strange, anti-up, or strange, anti-down. You have strange up or strange down. The up quark has got a charge of, I'm just going to check those. Up quark is a charge of +2/3, and the strange is -1/3. So that's -2/3 -1/3 is equal to -1. This one is -1/3 +1/3 is 0. So that's a neutral kaon, which is what you asked about. And that's the antiparticle of it. That's the other neutron kaon. So there are 2 neutron kaons, because one is strange anti-down, and the other is strange down, the other is anti-strange down. And you just have to know, because these are different particles, which is the particle and which is the antiparticle. And the rule is that the non-strange quark gets to decide. So that's a neutral, and that one's a neutral kaon, and that's an anti-neutral kaon. Question 30. Did I do the wrong question? Surely that is D. Yeah, I have got question D there. Right, folks, I'm going to leave it there because we've been going an hour. And yeah, that's all due to March. Okay, okay, got it.